4.3, which is patterns and nonlinear functions. So you're going to see this whole linear versus nonlinear thing, okay? And we've talked a little bit about that already. When something is linear, what is it? A straight line, okay? When something is nonlinear, it is not a straight line. So if you look at this, a linear function is a function whose graph is a non-vertical, because a vertical line is a straight line, but is not considered a function, or part of a non-vertical line. So basically any of these three, okay? The points, it could be points, we call that discrete, we'll talk more about that later, or it can be continuous. It can be a line that just keeps going. Shane, I'm over here. Do I need the ball? Just send me the ball. Push the ball over here. So if you can make, nice, just say you scored a goal. If you can make a straight line out of the information that you're working with, that is a linear function, okay? Assuming that line is not vertical. A nonlinear function means you're not going to have a straight line. There will be a curve or a turn or something that makes it not perfectly straight, okay? Which you can see right here. This U-shaped curve, that's called a quadratic. You don't need to memorize that. But that's like x squared plus 2x plus 6, right? That would be a U-shaped curve. That's what they're doing in Algebra 2 right now. This, right, not a straight line. It has that like kink in it, that curve in it that makes it not a straight line. This is straight lines, but it going in two different directions. Okay, so again, that is non-linear. If it is not one straight line, it is non-linear. Okay, so you're going to be distinguishing today between linear and non-linear given information. So it's going to be some graphing. And I think one of the most important things with graphing with this stuff is that you're counting your variables by a good number. I think that's kind of the trickiest part, really. Before we start graphing this first one, do me a favor, because I should have put a graph on the bottom one too, and I don't know why, but I didn't. Just copy and paste this graph that you see here and drop it down here before you start scribbling on it, or do it with the second one, whatever, just so you have a graph to work with on that bottom one too. All right, so here's what we're looking at. Example 1, okay, so we're gonna have two different graphs and try and figure out, are they linear, are they non-linear, is it one of each? What's going on with the information we're working with, okay? Is there a constant relationship to them? Because if there's a constant relationship, that means there's a slope, which means you have a straight line, okay? Which we'll get into more down the road. So this says the area A in square inches, that's this, of a pizza is a function of its radius r in inches. Okay, then it says the cost C in dollars of the sauce for a pizza is a function of the weight W in ounces of the sauce used. Graph the functions shown by the table. Is it linear or nonlinear? Okay, and some of you might see it just looking at numbers. I still want to see a graph. Okay, I want to see how this graph is working together. So, first of all, typically when you see a chart like this, which one is your X value? The one on the left. So these are going to be your X's. These are going to be your Y's. You want to label your graphs, and I'm sorry I didn't give you a ton of room here, but just zoom in a bit. Oops. So this is going to be radius. And the other is going to be area. Okay. Now look at your numbers, okay? Your radius goes as low as 2 and as high as 10. What would you count by on that bottom edge? You could count by 2. I wouldn't, but you totally could. Would anyone count by 1? I like to stretch my graph out a little bit, so I'm actually going to count by 1 just so that my graph isn't so like compact. So let's just do that for now. If you counted by 2, it's okay. Your graph's going to look a little different than mine just because of the scale of it. But there's plenty of room to do all 10 there, so I would do all 10. Okay, now here's the tricky part. we have to go as low as 12.57, but as high as 314.16. So the goal is make some numbers here on that y-axis that will fit all of them, but not like so tight that you can't really place a point. I'll tell you what I counted by in a little bit, but I'm curious, I'm gonna let you look at it for a minute and see what you feel like makes sense to count by. Now remember, you must count by the same number the whole way through. So we counted by ones here. We don't have to count by ones vertically, but when we go vertically, every single hash mark has to jump by the same amount. You can't just go, oh, I'm gonna start at 12 and then I'm gonna go to 40 and then I'm gonna go to 100, right? You have to count by the same number of units. What do you think? Did anyone find one that you're like, oh, this was great. I love counting by this number. To fit them all on there, but not be like right on top of each other, super compact. What?
50 maybe?
50? You could do 50, yep. Khalees. 37. You could totally do 37.
25.
Yeah, you could do that. I think it makes for more work when you pick a number like 37, but it's not wrong, and you could absolutely do it, and it would probably lay out pretty nicely for you.
25.
I did 25, because if you do 25, let me show you how this falls. If you go 25, 50, 75, 100, 125, 150, 175, 200, 225, 250, 275, 300, you end at 325, which is kind of perfect because your last number is 314. So that's what I did, but hear me on this. There is not a right answer here, okay? There's lots of right answers as long as your graph represents how you did it, okay? So I'm gonna do it this way just for the sake of everyone seeing it one way. But now here's what you do. You go to 12.75. So 2 to the right, 12.75 is about halfway to 25, right? It's a little bit more than halfway. So it doesn't need to be perfect, but close to the spot that we're trying to represent, right? So that would be about there. Your next one is 4, and then 50.27. That's essentially 50. When the gap between 50 and 75 is 25 units, and you're not even a whole unit away from 50, I'd pretty much put that at 50. So that's 450. Okay, then your next one is 6, 113. So over to 6, up to 113. 113 is about halfway between 100 and 125. So that's going to go there. Then it's 8, and then 201 is pretty darn close to 200. So 8, 200-ish, maybe just slightly above the 200. And then your last one, 10, 314. So 10, oh shoot, I messed up my 8. Hold on. And then 10, 314 will be around here. Okay, so the question is that linear? No, you cannot put a straight line through that. In fact, if you were to draw the curve, oops, that's terrible. I hear that. So this would be considered non-linear because it is not a straight line, okay? Now look at this one. What would you count by? Well, first of all, which one's your x? The weight. Okay, so that's going to go down here, your weight on the bottom. The cost is your y, so that's going to go on the side over here. What would you count by on your weight?
0.8.
On your weight.
Oh, by 2.
But count by, so you can count by twos. I'm going to count by one again, but you can count by twos. We don't need to go to 11. Okay, now, Henry made an interesting observation. He's going to count by 0.8. Why? Because everyone goes up by 0.8. If you want to do that, by all means, go right ahead, right? If you see that pattern, if you see that each time it's increasing by 0.8, you can totally count by 0.8. The trouble is, I think a lot of times people don't see that. So I'm going to assume that not everyone sees right off the bat that you're going up by 0.8 each time. And I'm just going to think what is reasonable here. So it goes as low as 80 cents, as high as $4. What's something else maybe we would count by? You could count by 1, okay? You could count by 50 cents, right? 50 cents, $1, $1.50, $2. Those are all good. They all work. I don't care which one you do. I just care that you're consistent. So if you're going to count by 50 cents, count by 50 cents the whole way. If you're going to count by 80 cents, count by 80 cents the whole way, okay? I'm going to count by 50 just for the sake of anyone who doesn't see the 80 right away. So if I'm going to count by 50 cents, this would be 50 cents here, $1, $1.50, $2, $2.50, $3, $3.50, $4, and $4 is as high as you go, so you don't have to keep going past that because we're not going to graph past that. And then you'll graph it. So 2 and 80 cents would be right about here. Okay, 4 and $1.60 is right about here. 6 and $2.40 is just below $2.50. 8 and $3.20 is going to be right about there. And then 10 and $4 falls perfectly on a crossbar. Would you say that's linear or nonlinear? That is linear. That one makes a straight line. Okay, so you're graphing and then you're telling me linear or nonlinear. Okay. Okay. This one is a little bit trickier in terms of what you want to count by, maybe. It says the table below shows the fraction A of the original area of a piece of paper that remains after the paper has been cut in half n times. Graph the function represented by the table. Is it linear or nonlinear? So you have your number of cuts. I'm going to move this a little bit. Oh, look at that. Just move it like that. So which one is your like X? Which one's on your X-axis? The number of cuts. Okay, so that's going to go down here. Always, always, always label what you're talking about. Okay, it makes it so much easier when you're trying to understand a graph if you know what pieces are what. So then the Y is going to be the fraction of the original area. Okay. What makes sense to count by on the X-axis? Counting by ones, right? You go 1, 2, 3, 4. So I'm going to count by ones here. 1, 2, 3, 4, and it only goes to 4, so that's as far as you need to go with it. Okay, now this one. This one is a little bit trickier. So you have 1/2, and then you have 1/4, and then you have 1/16. Can you wait till we're done? Or is this an emergency? I know, but this one's goofy. Do I know that you finished it correctly? What should we count by? Because you have to count by the same amount every time.
1.
You could count by 1/4. You could count by 1. If you count by 1, it's all going to be within this little chunk right here, right? Your entire graph. Because this is all less than 1.
You can
So-
count by like 0.25.
You count by 1/4.
1/6, or is it down?
What?
Like 1/6, or if your line goes down.
I mean, your line is going to go down. I wouldn't do 1/6 just because none of these are in sixths.
1/16.
I would probably do 1/16. Because here's why, okay? If I do, this is 1/16, this is 2/16, right? This is 3/16, 4/16, 5/16, 6/16, 7/16, 8/16. And we actually don't have to go any higher than that. What is another way of saying 8/16? 1/2. Okay, so this is technically, like, we're not even to the number 1 yet, right? The number 1 is going to be way up here. So all of this is just a fraction of 1, okay? So this is 1/2. Do you see 1/8? 2/16. This is 1/8, okay? Do you see 1/4? 4/16. This is 1/4 right here, okay? Which one am I missing? Oh, and 1/16 is right here. So then it's really easy to plot them because you have all of them as crossbars, okay? So if I go 1/1/2, I'm actually going up to 8/16. If I go 2/1/4, I'm going up to 4/16. If I go 3/1/8, I'm going here, and then 4/1/16 is right here. Is that linear? No, it's not changing by the same amount each time, right? We're curving. So we would say this is non-linear, okay? I'm telling you guys, the trickiest part of these problems is figuring out what you're gonna count by. If you struggle with that, talk to me. I'm happy to help you try to figure it out. But you wanna be broad enough that your graph isn't all right on top of each other, but not so broad that you get crazy, like, fall off the graph answers, okay? Questions on that? All right, that is all.